Sorry to be so soft-spoken. Sorry. The microcontrollers that you find in every electronic device nowadays has also gone into smoke alarms. What we need to do is to educate these microcontrollers to tell the difference between burnt toast and an actual fire. So we're introducing the smart smoke alarm that detects fire sooner than conventional home smoke alarms, and with fewer false alarms than the ones that are out there right now, but at comparable costs. So we're not talking about a very expensive gadget to implement. And what it does is we intelligently combine data from one or more sensors, up to 4 or 5 if we want to, different kinds of sensors that can sense the conditions at the time and can detect, just like your nose would, a fire from a non-hazardous condition. And what we use is a mathematical technique called linear discriminant analysis, and that's a highfalutin technique that looks for patterns and tries to optimize categories of responses according to what it sees. In other words, what is that smell? What's it due to? And what we do is we take data using these sensors that are embedded in homes and manufactured homes and test fire setups. So that hundreds of fires have been set off, and these sensors have been watching what's going on, recording the data, and we take this data and distill it into a database that trains this linear discriminant to know the difference between a real and a false fire. And what we, in effect, give it is a kind of a discriminant space map, we call it, so that it knows where it is. It's normally in a normal condition, but there are different types of fires that appear in different areas of this discriminant space. This is something that you wouldn't see, but it understands that within the microcontroller. But nuisances appear a little bit off from normal, and we can squelch those kinds of alarms. What we've done to date is build a prototype that, using sensors that are taken from commercial smoke alarms. So these are inexpensive sensors that are well proven. We've built our own printed circuit board to analyze the signals that come out of here. The little microcontroller is about as big as your little thumbnail, and it costs less than $1, and that's what's commonly used in smoke alarms nowadays. And printed that in a plastic housing so that it looks like an ordinary smoke alarm, but inside it has some different stuff. And what we're trying to do is optimize the algorithms to understand the difference between the different types of fires and nuisances. The development risks are fairly low because we've already demonstrated part of it, and by modeling the situation, we've determined that it can recognize smoldering fires in particular 20 or 30 minutes faster than a conventional smoke alarm. That's pretty important safety margin to build in. So the development costs or risk are fairly low and just depend on the calibration of the sensors. Where we're coming from here at Ornell is we've built a set of fairly complicated analytical gear. The CBMS is an $80 million project to implement a mass spectrometer in a field situation so that a soldier is aware of the chemical and biological hazards that are out there. He doesn't want to look at a complex mass spectrum and trying to interpret that, so you have to have a mathematical algorithm to understand that. We built a sniffer for the Department of Homeland Security to give first responders an awareness of toxic industrial chemicals in the environment. This used an entirely different set of sensors, electrochemical and mobility spectrometry and so forth. And in a little handheld instrument, this ChemRing Juno product is designed to look for chemical warfare agents and for toxic industrial chemicals. All three of these use the same type of mathematics. as the smoke alarm that we're using. Whereas commercial smoke alarms still use simple threshold sensing. Once the smoke gets above a certain level, it just goes off. It doesn't know any more than that. So by modeling the early investigations we've found, by modeling numbers of fires, these are data that this is several dozen different types of fires, smoldering fires in particular, we found that we could sense that smoldering fire in an alarm with confidence 20 or 30 minutes sooner. In fact, 60% of the cases in smoldering fires, we were about 30 minutes faster than a conventional alarm. The flaming fires come off in 2 or 3 minutes, and so we have about the same advantage there. We've got a little work to do on the grease fires, and we discovered that there's a deficiency in the way the data was taken in the field, and that's throwing us off. So we can modify that and fix that, we think. The previous slide showed a sensor, a smoke alarm device with 4 sensors in it. That's the complete suite. But even if you take all the sensors out but one, the photoelectric sensor is what most of us have in our homes anyway. Many of us do, particularly in the kitchen, because these things don't tend to go off as often as ionization alarms. If you take that and analyze the signals, you've got one signal to work with. Well, you can take the rate of change as well with a microprocessor. And again, you get a big performance increase in detecting smoldering fires. It does as well as the conventional photo smoke alarm, but it gives you an advance warning, especially for smoldering alarms. So we've gained about a 20-minute average improvement. The nuisances aren't really suppressed so much, whereas previously we had, on this alarm, we had not only faster detection, but complete elimination of nuisance alarms in at least half the cases, and in all cases, it was much slower to alarm. So we've increased our performance there. Haven't so much in a single sensor case, but it just shows that a little intelligence can improve a smoke alarm at essentially no cost. And so what we're trying to do is in the next month is to optimize our algorithms and implement those in a microcontroller, produce a full suite of fully functional units so that we can demonstrate this to manufacturers, hand them off as samples, test them in your own lab. We want to do validation testing at Underwriters Laboratory. That's where all the smoke alarms are validated, and to show that this passes all the UL tests. That would be very important for a manufacturer. So the key challenge is to make sure that these smoke alarms work as well or better in all cases to conventional alarms. And so we plan to validate with UL, as we just said. We want to publish and present these results around development technical tutorial so that people know how they can build their own LDA, their linear discriminant analysis, using and customize their own products so that they can have their own crowing points, let's say. So we want to produce demonstration units and get licensees to look at these and get them in the field. The partners that I've listed here are the 3 biggest manufacturers of smoke alarms, Kitty, First Alert, and Universal. But we're talking to some smaller firms as well, a couple of smaller firms, and any other newcomers are welcome to make inquiries. We could possibly extend the same kind of algorithms to commercial units. A different set of companies would be open to that. Instead of having small detectors, that would be a fire control panel program. And so you could think about different models that could be introduced. The basic model would just be an entry-level product that would be essentially no additional cost, whereas right now we have just single sensors with thresholding we could add a smart control to improve the performance. If we added another sensor like an ionization or a photoelectric, we could improve the performance for a little more safety-minded consumer. Getting into toxic gas detection is a very popular topic nowadays, but we can use that carbon monoxide sensor not only for toxic gas protection, but for early sensing of fires. Carbon monoxide comes off as a combustion product in nearly all fires, and so it really improves the performance of it. Or we could put the full set of sensors in for a complete high-end product. So all smoke detectors have smoke detection. Okay, that's built into the name. Most models have toxic gas options available or companion products that you can look at for toxic gas protection. Some of them even try to claim they get some enhanced fire detection because of that. In fact, Kitty has one product that uses carbon monoxide to increase the sensitivity for its fire detection. But the nuisance rejection and that sort of product, that sort of quality is not really seen in most of the products. They all say nuisance rejecting or that sort of thing, but when you bring them into your own kitchen, you find out something a little bit different. And another feature that we built in to this device is a low-frequency alerting system. Instead of a high-frequency sounder, which operates at 3,100 hertz, that's a kind of an ear-piercing thing for most of us, but it doesn't wake the elderly and children nearly so much. So a speaker operating at 500 hertz is found in studies to be dramatically improved for alerting people, particularly the elderly and children. So there's hundreds of products out on the market. The annual sales is about 20 million units per year, or about $500 million. And since our technology is adaptable for even single sensor units, there's really no cost, incremental cost at least, and so none of the market is really excluded, even the low end. Of course, you might have higher performance models at the onset. In fact, the Nest model has just been announced and not on the market yet. It sells for $129, so there's a market for a high-end system. And it talks about nuisance rejection, but the main crowing point is when the nuisance alarm goes off, you can just wave and it shuts up. So that's an improvement, but you'd rather not be bothered. One of the key features of multiple sensor alarms is the complexity that you need to program into the algorithms. And so future standards for fire detection, they're being talked about such that single sensor alarms are unlikely to pass. Okay, you'll probably need to make a more complex alarm to pass UL standards in the future. This is an easy path to programming multiple sensors in an optimal fashion. And of course, awareness of carbon monoxide risk will help drive models that also have that functionality built into it, both for toxic and for fire detection. Well, as I said, since 1975, the number of fire deaths has been cut in half. But look at the statistics. In the latest year that's available, 381,000 fires occurred in homes. 2,400 lives lost. It's been as high as 3,500 in the last few years. Injuries, nearly 13,000. Property loss of $7.2 billion. Would an insurance company be interested in advancing a product that would help them save property and losses due to lives? Sure they would. One of the things that you find is that residential construction methods and furnishings have changed. Foams and that sort of thing are been put in the house. So in 1975, whereas the average safe egress time was 17 minutes, it's reduced to as little as 3 minutes now for a fast flaming fire in 2008. So it's very important to get early warning, get out of the house as fast as possible. And I've been here for 35 years, worked on a lot of different projects, but if I could have a hand in getting a product to market, I think my tenure here would be worthwhile. So I think this is a very important advancement that will affect the lives of millions of Americans if we can just get it out there. And alerting can be sometimes problematic. The news of this kind of carries, and we're not too familiar with fires ourselves. Most of us have never experienced a tragic fire, and hopefully we never will. But of those that do, the firefighters have come to me and asked, when is this thing going to get in the market? When can we see this sort of thing? So it's important to get it out. Anyway, I'll stop and ask for questions. Yes, sir.
What are the main claims in your patent?
Well, it's the application of the discriminant algorithm. Basically, that's the central feature of that. And I can't go into all the details of that, but that'll be fully disclosed and taught as a for license transfer. Yeah. Yes.
What about networking? So you're not going to have just one of these fire alarms in the
Yeah.
house, right? So you can use Bluetooth and all these other networking systems, and increasingly more customers have cell phones as well that connect through Bluetooth. So
Right.
you can even pair the devices to the phones as well. Most people might look up their phone, or you might even bypass with an app
Yeah.
to ring a special alarm to the phone should they be sleeping or be at a certain time. I'm just saying, if you're going to introduce software to discriminate, why not also introduce software that networks and to network also with departments, fire departments?
Oh, that's a good idea, and I think that's just beginning to appear. The Nest, for example, is starting to capture that same thought, being on a Wi-Fi network, going to your cell phone to pick that up. So I think that's something that'll appear, particularly in the higher end market. But yeah, that's the sensors are dirt cheap. Yeah, each component is the order of $1 or less. When you put a few dollars together, then you got to go through marketing and quality control and everything else, and now it's $100. So it does add up pretty quickly. Yes.
With the additional sensors, is there additional power that would prevent them from being powered in a semi-permanent 9-volt fashion, or would require a hard wire?
No, these are all low power units. The carbon monoxide sensor is the same sensor that's used in the kitty unit, for example, and the other units are all low power. So we're using just 3 AA batteries in here, just about like the kitty model is. Photoelectric ionization, temperature, and there's the carbon monoxide cell. These things will have a lifetime of about 10 years. I might, since I've promised to blow a little smoke, let's see if... Are we going off? That's the trouble with demos. This thing has never failed. Never failed. Never failed. Huh. I've done this hundreds of times. There we go. Thank you. But you hear the low frequency alarm that's coming out of that. I've muted it. It should be about 85 dB, so that would be a little more ear splitting. Sorry. Yes, sir.
Are you testing the prototype against incense
Yes. We have not. The incense is likely to produce very little carbon monoxide, and so that'll be a telltale. thing. These are nuisances that aren't in our test suite right now, and so we need to check those out. Hamburger, bacon, pizza, spaghetti, dust, all sorts of things, but we need to add to that repertoire. The advantage to the method is that if you continue to make more tests, you can make the database more complete, the algorithm more robust, but it always centers around the most optimum classification that's possible based on the known test. Yeah. I think we'll find out with time. Yeah. Yes, sir. Well, generally they're on the package when you get them. If you bought them in your home from a contractor, then they're probably going to be the baseline ionization units. These things can be bought for as little as $5, and so it's really hard to compete with that sort of thing. It's important that you check them. They advise once a month. Just push the little button that gives you the basic circuitry operates. The battery is still there, and it's basically functional. And every 10 years or so, you should probably change your fire alarms. Putting one in every bedroom, everywhere someone is sleeping, putting one in every room, and that's the basic recommendation that you should all be watching. They typically are not, unless they're the higher cost units. These are about carbon monoxide units start at about $30, $30 to $50, and that sort of thing. So they're typically not. They're basically just the smoke. They call them smoke detectors because that's mainly what they detect, just smoke particles. Yes, sir.
Yeah, you take the lid off and look at the serial part number inside of the bin and Google it.
Yeah. All right.
You mentioned that you use commercially available sensors in your prototypes.
Right.
Now, are those sensors you take from other smoke alarms that might have to be commercially licensed or remade for an application? Or are these off-the-shelf parts that you use with them?
These are not available at DigiKey. These are taken right out of smoke alarms. So each manufacturer builds his own sensors. He would take his own sensors and create a product. Basically, he just needs to take his smoke alarm and educate the smoke alarm with this algorithm based on the performance of his sensors. These are all calibrated in terms of obscurance units or carbon monoxide parts per million, and so this can all be normalized. And each manufacturer can make his own algorithms based on his own sensors.
One more question.
Okay.
There's a commercial smoke and carbon monoxide detector coming on the market by a company called Nest.
Yeah.
They retail around $120.
Right.
It's not as sophisticated as what you displayed, but it's designed to eliminate the nuisance alarm by a simple wave of the hand and not a fanning, just
Right.
wave. And it can also pass information on the smartphone, things like that. Have you had any opportunity to look at cost comparisons as to what it might, how your product or your technology is developed into a commercial product might compare cost-wise?
For the same set of sensors, it really shouldn't cost any more. Okay? If you have one sensor, it's going to cost about the same as a one sensor alarm, $20. For something that has more sensors in it, or it has the Wi-Fi component and that sort of thing, like the Nest, then it's going to cost a little bit more. It'll demand a little higher market, regardless of the cost of the parts.
But you're expecting it about the same price range.
Yeah,
That's a
right.
final problem.
I am trying to get in touch with Nest so that I can embed. These are smart people. These are people who developed the iPhone, a couple of execs there, and so if I can get their attention and put that algorithm in there, then they would really have a smart device. Yeah.
Thanks again.
Okay, thank you.
So at this point, we're going to